All right, welcome. Hope you guys are having a good week. I am going to spend a little bit of time talking about the content that you're going to see in 12.1, 12.2, and 12.3. This content is going to be a lot more heavy on computations and is going to be something we use a lot in the coming unit to help us simplify our answers when we're dealing with quadratic equations. I do want to point out that this material is not on test number 2. So if you've not taken test number 2, just know that this material is not on that test. This will be on the next test, test number 3. All right, so I'm going to introduce you guys to this letter variable that's used in math. I will tell you that in this class, my math labs uses the letter J. In most textbooks, the majority of textbooks, J is not the letter that's used for this. The letter that's used for this is I. And so that's a decision they made. But in this, just know if you watch any other videos on this, or when I do this, I am going to use I. Just know that they're using J instead of I, but it's the exact same idea. And so you might see me go back and forth, but because I'm so used to using I in all my other classes that sometimes I forget to use J. And then we'll talk about what a complex number is, because that is vocabulary you're going to see. So let's talk about this number and why we need it in mathematics and where it came from. And so I want you to consider two basic equations. Let's consider the equation x squared equals 36 and x squared equals negative 36. And so these are two equations that are very similar with very different answers. And some of you might remember this from previous math classes. For some of you, it might feel like you're seeing this for the first time. But if you take a look, what this is saying is basically there's some number x that when I square that number, when I multiply that number by itself, in the first equation, I'm getting 36. And in the second equation, I'm getting negative 36. Okay? And so the 36 one is an interesting equation in and of itself because there's actually two values that will make this a true equation. If I think about I'm squaring a value, how do I undo that? In mathematics, every operation has an inverse operation. And so what is the inverse operation of taking a number to the power of 2? And the answer is to square root. And so if you're thinking about solving this by doing the same thing to both sides, as opposed to just guess and check or thinking about it mentally, which many of you probably have already solved this equation, then you can think about it as a square root. And so I'm going to take the square root of both sides. Now, because we are solving equation, the square root of 36 is 6. So if this was just an expression without an equal sign, and I said, what's the square root of 36? Then you would just say 6. But because this is an equation, I have to consider all values of x that make the equation true. And so there's actually two answers here. I'm going to say that x can be 6, but x can also be the opposite of 6, which is negative 6. Because if I do 6 times 6, or 6 squared, that does give me 36. But negative 6 times negative 6, or the quantity negative 6 squared, is also going to be positive 36, because a negative times a negative is going to be a positive. And so these are our two solutions. And you're going to see this in the coming unit, or in this unit in the coming weeks, that there's always going to be two solutions when we solve a quadratic equation. Sometimes there are instances where we'll get the same solution 2 different times, but in general, we're going to say there's always 2 solutions to any quadratic equation. And by quadratic, I mean anything where we have like a variable being squared. Okay. Now, the next expression is the reason that J or I was developed by a mathematician. There is no number such that when I square x, if you think about the range of the graph of x squared, x squared looks like this, right? It's this parabola looking thing. But notice that the range here is only in the positive, so it's only positive outputs. Here, this here is a negative output, and which means that I'd be looking down here. And you can see that the graph of x squared, it doesn't have any values down there. So there is no value for x, no value for x such that when I square it, I will get a negative 36. Again, because negative 6 times negative 6 is positive 36. And so some mathematician came along and saw this and ran into this and said, well, let's make something up. Sometimes in math, it's okay to do that. It's not always okay to do that. But in this case, he came up with a system to handle this. And this system is very elegant and it's very convenient. I don't know that any of you will appreciate it as much as I do as a math teacher because it's just more work for you. But this is a very, very interesting solution to this dilemma that he came from. And so he said, well, let's just do this. Let's come up with this number. And let's make this number I. Okay. And let's do this. Let's say that I squared, and this is the more important idea here, or I guess this is where we start. If I square this I, whatever this is, and again, your book is going to use J, but let's just say I take I and I square it. That should give me negative 1 every time. Okay, so whenever I see I squared here, I should be able to replace it with the value negative 1. And so if I solve this equation the same way I solved over here, and I square root both sides, then that would mean that I, because the square root of I squared is just going to be I, then I is going to be equal to this number, the square root of negative 1. And again, just like the square root of negative 36 has no value, there's no value that I can square and get negative 36. It's the same thing with negative 1. Because when you square root a number, you can only get out positive values. So we can only square root positive numbers. So we know this now. We know that, I'm going to get rid of that. We know that I squared is going to have the value negative 1. And then I is going to be the same as the square root of negative 1. Okay. Now, these two ideas here, are what are going to kind of drive this entire unit here. And so, again, I squared is going to be negative 1. I will be the square root of negative 1. Now, the square root of negative 1 has no value. If you go into your calculator and you type the square root of negative 1, it's going to say non-real answer or error or something like that, okay? But we'll just leave it as a square root of negative 1 for now, okay? And so you can see, again, you're not going to do this in this section. You're going to deal with only expressions, not equations. But in the next section, we're going to get to where we need to be able to handle this. So now what I'm going to do is I'm going to take the square root of both sides here. Okay. Actually, I'm not going to solve this yet. I'm just going to tell you the answer. So the answer here is going to be 6i or negative 6i. I'm not going to explain why. I'm just going to prove to you that this is a solution that will result in a true equation. And so I'm just going to use this one here. I'm going to take 6i and I'm going to plug it in here for x. And I'm going to prove to you that based off of these rules that I've boxed here, this will result in a true equation. And so I'm going to square the x value and I need to get out negative 36. So I'm going to take 6i, I'm going to plug it in there. Okay. Well, 6i times 6i is going to give me 36i squared. And you can see, if you're tracking what I'm doing, you can probably already see the next step, but we know what I squared is. We know that I squared actually does have a real value attached to it, okay? I does not, because the square root of negative 1 is a non-real value. We don't say imaginary, although that's what you're going to hear a lot of teachers say. We just say non-real. Okay, because when people think about imaginary in the English language, they think about something that doesn't actually that's pretend, right? And this is just we're going to say it's a non-real answer. And so I squared here is going to get replaced with negative 1. And so you can see how this is going to work. We're going to finish here with 36 times negative 1 is equal to negative 36. And so negative 36 is equal to negative 36. And so I've proven that 6i will work. If I do negative 6i, I'm just going to tell you, you will also get negative 36. So again, you're going to see those two solutions there. And so this is the reason that this value here, j or I, whatever you want to call it, was was created by a mathematician. You can see it kind of solves this problem for us. Again, I didn't show you how to get that from solving. We'll cover that later. But you can see when I plugged in 6i, it actually resulted in negative 36. And that's what solving an equation is. So we now know that I squared is negative 1. And we know that I is the square root of negative 1. Well, what happens if I take I to higher powers? Okay. And so let's talk just a little bit about that. And again, you're going to see this, right? And so let's just look at the following values. Let's take I to the 4th power. Let's take I to the 6th power. We'll go 9, and then I'm going to get crazy here, and let's go I to the, I don't know, 57. Okay. All right, now the only thing we know for sure is that I squared is negative 1 and that I is the square root of negative 1. That's all I know. So when I see I to the 4th, what I'm going to do is I'm going to get a little tricky here. And I am going to, you know what, before we do I to the 4th, let's do I to the 3rd, okay? Just so you can kind of see some pattern recognition here. And so I to the 3rd is where we're going to start. And if I take I to the 3rd can actually be broken up into two things I know. I know what I squared and I know the value of I squared and I know the value of I. And so what I'm going to do here is I'm going to factor this, okay, into two things I know. And remember, when we factor, that means that when I take the product of these two factors, it should get me back to where I started. And so I'm going to factor this into I squared and I. Okay, I squared times I is going to be I to the 3rd power. So this is equivalent to this up here. Okay, but now I can break it into parts that I actually know the value of. I know that I squared is going to be negative 1. And then I can go ahead and put the square root of negative 1 in here. But what I'm going to do, and you're going to see me do this, is I'm just going to leave I like that, knowing that I represents, again, that I doesn't represent negative 1. It represents the radical or square root of negative 1. But this simplifies this expression into the opposite or negative I. And so I now have this other property that I can add in here. I can now say, well, guess what? If I have I cubed, it's going to be negative I. Okay. And then we'll do this one more time with I to the 4th, and then we'll try to use these 4 values of I to kind of find bigger values, I to the bigger powers. And so I to the 4th, I can break this up a couple of ways. I can either break this up into I cubed times I, because now I know what I cubed is, and I know what I is, or I could break it up into I squared times I squared, and that's what I'm going to do. Okay. So again, I squared times I squared is I to the 4th. When you're multiplying two numbers together, if they're the same number, you can add the exponents. And so this is going to turn into negative 1 times negative 1. Well, what's negative 1 times negative 1? Well, that's just 1. So we can see that there's different things going on here, and some of the patterns going on here is that if I take I and squared, I get negative 1. If I take I and cube it, we've shown that it's negative I. And then the last one here I'm going to get is I to the 4th, which is going to be positive 1. Okay. And so these are the 4 that I would use. If when you're doing this, and if you're watching this video, this should make this a little bit easier for you. But those are the 4 values I'm going to use. And so what I'm going to do is I'm going to get a little tricky here. And I'm going to kind of use this fact that I to the 4th is just 1. And so when I do I to the 6th here, I'm gonna try to use that as often as possible, because when I multiply a number by 1 times 1 times 1 times 1, you can see that that's just going to be 1. That's not going to change the value. So this is called an identity. I to the 4th is the identity, meaning that when I multiply a number by I to the 4th, it doesn't change its value, because I to the 4th is really just 1. And so I like that. And so whenever I can, I'm going to use that. And so I to the 6th is going to be I to the 4th times I squared. And so I to the 4th is 1. and I squared is -1. And so I to the 6th is -1. Okay. I to the 9th, I'm going to have to break this off into I to the 4th. Again, I to the 4th is my favorite, so I'm going to use that as often as possible. And then this will be I to the 5th. Okay. Now, I don't have in my table I to the 5th, so I'm going to keep breaking that down further. Again, you can do I squared times I cubed. I'm going to use I to the 4th anytime I can because that's the identity. That's just 1, so that's going to be my favorite. So now I've got 1 times I to the 5th, and I can break that down even more. And now I've got 1 times I to the 5th is going to be I to the 4th times I to the 1st power. I to the 4th is 1, and so what I really have here is 1 times I, which is just I. Okay. And again, could I put the square root of -1? Yes, you could replace that with the square root of -1. But again, in my math labs, you're always going to want to leave your answers in terms of I if there are any I's in your final answer. Okay. So I used I to the 57. This is the last one I'll do here, and then we'll move on to complex numbers. But I to the 57, it's going to take me a long time to use this same algorithm, right? To keep breaking down force is going to take a long time. So what I'm going to do is I'm just going to do a little elementary school math here, and I'm just going to say, well, let's see how many 4s I can take out of 57. Okay. So 4 goes into 57. How many complete times? Because every one of those times is just going to be an I to the 4th. Right? And that's just going to be 1. So 57 divided by 4, well, 4 goes into 5 one time. So we'll do a little, again, math here, and that's going to give me 1. I'm going to carry down that 7, and 4 goes into 17 4 complete times, right? Because 4 times 4 is 16, and that's going to leave me with 1. So remember, this is an exponent, so this is going to be my exponent. Okay, the 14 here is what we call the quotient, and this here is called the remainder when you're doing these problems. So the quotient, this is the number of I to the 4th powers I would actually do this. So you can see here, the 9 here was broken into 2 I to the 4th. So I had an I to the 4th here and an I to the 4th down here. Because 4 goes into 9 2 perfect times, right? And so every time I pull out an I to the 4th, that's just the number 1. And so what I'm doing is basically saying, well, I can pull out 14 of these 1s, right? And so what this really becomes is 1 times 1 times 1, 14 times, right? Times what's left? Well, I, and the remainder here is 1. So I've got 1 I to the 1 left. And so these 1s are just going to be 1. They're not going to change. Again, there's 14 of them, okay? But it doesn't matter how many of them are, because 1 times 1 times 1, as many times as you want, is still just going to be 1. So what I'm left with here is just I. If this was I cubed, that'd be fine. Again, you couldn't put I cubed. If it was I cubed, then I would reduce that to -I. If I get I to the 4th, then that's going to be 1, right? If I get I squared, then that's going to be replaced with -1. So when you do this in my math labs, every one of your answers should be something like this, 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 or this. All your answers should look like that. Every single one of your answers when you do these problems of I to some power should be I, -I, 1, or -1. It's not simplified until you've basically gotten to one of those 4 answers. All right. So now let's talk about the definition of complex numbers. And sorry, I'm just going to check the time to see how we're doing here. Okay. I think I can get through this part pretty quick. This is going to be a little longer video, but I think I'm just going to do it in one video instead of 2. So a complex number, okay, again, when we talk about I, this is what we call a non-real number. Some teachers will say imaginary, some textbooks will say imaginary, but non-real is going to be the most specific, okay? All right. And so let's talk about a complex number. So when a number is complex, then that means it's made up, okay, of both a real number, and a non-real number. And so you see this a plus bi or a plus bj. The a represents the real number. So 5, 6, okay? The square root of 17, whatever you want that to be, that number does not have an I attached to it. And then the non-real number here, okay, is going to be whatever that coefficient is in front of the I, the b value, okay? Now, all non-real numbers can be represented as a complex number, okay? The big thing you're going to use here when you do this is the I squared. Remember that I squared is equal to -1. So I'm going to go through 2 quick examples, and then we'll be done with this video. So simplify the complex expression, okay? And this time I think I'll try to use J, just so you can get used to saying that. Okay, so here we go. So let's say I have something like this. Okay, let's go 4 plus 2j, right, minus, okay, 5 minus j. Okay, kids were being a little loud there, apologize. So what we're going to do here is just simplify this like any normal expression. And so you can see I've got 2 complex expressions and I'm being asked to subtract them. And so this is pretty simple, or I shouldn't say simple, but it's basic, right? All I'm going to do is I'm going to combine like terms. So in this case, the 2 real numbers in there are 4 and 5, and the 2 non-real values in there are 2j and 1j, or just j. Or you can argue that it's a negative j. And so whenever I subtract a quantity, meaning there's a minus with parentheses, I am always going to treat this like a -1 and distribute this through there. And then I'm just going to rewrite this without parentheses. So I've got 4 plus 2j. -1 times 5 is going to be -5. And -1 times -1j is going to be positive 1j. And now I can just combine my like terms. So 4 minus 5 is going to be -1. 2j plus j is going to be 3j. And so my answer here is a complex value. And that's simplified. I cannot combine those 2 terms together. Okay, so that's one basic example. The other one, let's go ahead and take a complex number and square it. And then I'll do one more where we have something in the denominator, because you are going to see that. So if I have, let's say, 4 minus 2j, and that quantity is being squared, okay? Again, when I am done, my answer should be in the form a plus bj. So there can't be any extra terms in there, okay? So when I square this, this doesn't mean square the 4 and square the 2j and you're done. You actually need to write it out, and you're going to have to do what some teachers call the FOIL method. And again, there's a lot of different methods that it's the binomial times a binomial. I generally just use what I call the FOIL, and many other teachers call the FOIL. So 4 times 4 is going to be 16. Okay. Then we got the last times the last. That should be a 2. -2j times -2j is going to be, and I'll put this here at the end, it's going to be positive 4. J times j is going to be j squared. So now we see there's that square, and we'll deal with that in a second. And then we got to do the inner here. -2j times 4 is -8j. And then the outer is 4 times -2j is -8j. Well, the -8j's can combine, and so that gives me 16 minus 16j, but then I have this plus 4j squared. Now remember, if you plug that answer in, it's not that that answer is incorrect, it's just not simplified all the way. We have to have an answer in the form of a plus bj. And so the term that we got to do something with is the 4j squared. And so we can use the fact that j squared, I squared, remember that's the same thing, is the same thing as -1. And that's the little trick we're going to use to kind of handle this. So I'm going to go 16 minus 16j plus, now 4j squared is the same as 4 times -1. And so that value is a real value that becomes -4. And now my final answer, 16 minus 4, can be combined to be 12. And so now I have something in that form. Okay. All righty. And so that's a little introduction to complex expressions. I think this video has been plenty long, so I'm going to hold off on doing anything with I in the denominator. And I'll do a quick example. It'll only take me 1 second. 1 more minute. Okay, maybe 3 minutes, but stay with me. So the thing with simplifying complex numbers is you can have no non-real values in the denominator. Now this is just since this whole system of J's and I's was developed, these rules were also developed. And so this was just the rule that some mathematician came along, I guess maybe to make your life more difficult. But to be totally simplified, we cannot have non-real values in the denominator. So let's say I have here 4 divided by 2 plus I. We'll keep it simple. Okay. So if it was 2 plus I over 4, you could just leave it that way, right? If this was, 2 plus I over 4, then what I could do is say, well, that's the same thing as 2 over 4 plus I over 4, okay? And I would be done because my non-real value would be up top. But if you have a non-real value down here, then you cannot leave that in your answer. And so how we're going to deal with this is we are going to multiply by kind of the same way you used to get common denominators. You would multiply by the same thing on the bottom and the top. Okay. And we are going to multiply by what we call the conjugate. So multiply by the conjugate. Okay. Now, the conjugate of a plus bi is a minus bi. Okay. If I have like negative a plus bi, okay, then that'll be negative a. Notice the real term doesn't change. We flip the value of the non-real term to get a conjugate. And this is a little trick that will help us, and you'll see how, it will actually get rid of that value down below. And I'll show you how. If we do, 4 times 2 minus I, 4 times 2 is 8, and 4 times negative I is negative 4I. Okay, so we're okay there. Again, it's okay for I to be on the top. It's not okay for it to be on the bottom. Now what I'm going to do is go ahead and FOIL this again. 2 times 2 is going to be 4. I times negative I is going to be negative I squared. And then if I do I times 2, that's going to be positive 2I. And then here's the trick that always happens when you multiply by a conjugate. 2 times negative I is going to give me negative 2I. That is a real term. This is eventually going to be a real term when I use my I squared property. And what always happens when you multiply a complex number by its conjugate is the imaginary terms always cancel each other out. This will always happen. And so what we get here is 8 minus 4i. 2i and negative 2i go away. This becomes negative. Now be careful here. Negative I squared is the opposite of I squared. I squared is negative 1. So negative I squared actually turns into positive 1. And 4 plus positive 1 is 5. And so my final answer can be written like that, or you can go ahead and break that up into its part and say, well, that's going to be 8/5 minus 4/5 I. And I can't remember which one of these My Math Labs likes, so you'll have to do a couple problems to learn which one it prefers. All right, I apologize for the long video. There's a lot of information in this unit. I hope that helps. Please feel free to contact me if you have any questions. Again, none of this is going to be on test 2. So if you've not taken test 2 yet, please don't add this to your repertoire of need to know. You can work on this unit after you've taken the test. I hope you learned something, and let me know if y'all need anything. Have a good day.